Topic 4.3 Grain size determination. There are a number of techniques can be applied for the determination of grain size, and that is to ensure that the mechanical properties of the metals can be predicted related to its grain size, and also will be used as the guideline for quality assurance and also for product development. And one technique that I would like to introduce here is the determination of grain size following the ASTM grain size number according to ASTM E112, and that you can find it online. According to the ASTM, or American Society of Testing Materials, the grain size number can be determined according to this equation, where capital N equals 2 to the power n minus 1. Where capital N is the number of grains in square inch at 100 magnification, and small n is the ASTM grain size number. And if you look at the information from this table, the grain size number can be ranging from 1 up to 10, and each number is related to the nominal number of grains per square millimeter at 1 magnification, as you can see in the middle column. But then the column to the right, the ASTM grain size number is related to the nominal number of grains per square inch at 100 magnification. And as the grain size number increases down the table here, the number of grains also increases as well. And therefore, the larger the grain size number, the greater number of grains within the predetermined area, and therefore, the smaller the grain size of the metal being measured. The images on your right-hand side with varied grain size, as you can see over here, running from grain size number 1, 2, 3, 4, 5, 6, 7, and 8. And hence, you can see a trend of increasing number of grains towards larger grain size number. And if we compare the number of grains between two grain size numbers, the first one is grain size number 4, and the second one is grain size number 7. You can see that there would be 1, 2, 3, 4, 5, 6, 7, 8, approximately 8 grains within a square inch. That is conformed to the information when we look back to the information on the table here. But then, at the grain size number 7, there might be 64 grains altogether within the area of 1 square inch over here. And of course, the metals having grain size number 7 is expected to give better strength and ductility than the one that having the grain size number 4. And then I would like to give you the example how to calculate or determine the grain size using ASTM standard. For the determination of grain size using ASTM standard, there are 64 metal grains counted in a square inch from a micrograph taken at 100 magnification. And the question is, what is the ASTM grain size number of this metal? So from the equation, the capital N equals 2 to the power n minus 1. And what we have given is the capital N, which is 64 grains counted in a square inch from the picture taken at 100 magnification. So we have n as 64. But then the question is asking about small n over here. So it is more convenient to take log onto this equation all the way through. Therefore, we arrived at log 64 equals in the bracket small n minus 1 times log 2. And for the calculation, we have 1.806 equals in the bracket n minus 1 times 0.301, and therefore the ASTM grain size number of this metal is 7, and that is fit onto the information given in the table here. Therefore, the small grains will give good strength and ductility, and on the other hand, larger grains tend to make the metal behave in a brittle manner, and that is having more chance to fail in service. For engineer, refined grain size or small grain microstructures are more preferable for engineering applications in service at normal condition or at room temperature. And that is, the grain boundaries will give the strength to the metal while working at normal temperature. But then, if you remember in the case of turbine engine, at very high temperature, the grain boundaries are not desirable then. So, we have to understand the roles of the grain boundaries at different conditions and temperatures. so that we can properly select appropriate processings and heat treatment to obtain the microstructure that we want for the application that we have designed at the first place. There's another technique that nowadays we can use for the determination of grain size, and that is the grain size measurement by image analysis. And here we need the digital image taken with good resolution, and that can be uploaded into the software for the analysis of grain parameters. And for example, from the microstructure of equiax grains over here, the software can give us the parameters such as equivalent grain diameter or D, or even the grain area or A, the maximum length of the grain and the minimum length of the grains, as well as the aspect ratio, which is the maximum length over the minimum length. And in this picture, showing that the software can differentiate the grain boundaries, and that is the information can be used for the analysis of equivalent grain diameter, grain area, maximum and minimum length, and also the aspect ratio. As I mentioned earlier, the information like this is also important for the development of the alloys. There are many factors affecting the size and shape of the grains. And normally, in normal condition, we would like to have fine grain structure of metals. And in order to achieve fine grain structure, there are several techniques in the processing. First, for the metals that is produced by casting technique, fast cooling is going to give the finer grains upon solidification. As the rate of grain degradation is very quick, that we will end up with numerous grains in the microstructure. All the microstructure has the refined grain. Another technique is to apply inoculation. It is to add the seeding agent to produce numerous nuclei. And as you can see from the simulation pictures over here, once we pouring the molten metal into the mold, first numerous grains nucleated on the mold surface. Then on the cooling, the solidification rate is slower on the top over here, then we end up with larger grains as opposed to the grains that is subject to fast cooling at the first stage of solidification. And this type of microstructure is not desirable because we have non-uniform microstructure, and area on the top here is prone to brittle failure. And that's why we have to employ inoculation. That is to add the seeding agent to produce numerous nuclei. That is to suppress large columnar grains over here. So at the end, we will get just the small finer grains like this. And that is better to control the mechanical properties of the metal. And here are the techniques used in the process of metal casting. And for the metal processing that involves working operation, for example, one like this, that the metal slab is subject to hot rolling. In this situation, the larger metal grains are subject to high temperature and plastic deformation at the same time. To this, it will result in recrystallization as a result of temperature and deformation simultaneously applied at the same time. The obtained microstructure is the refined grain size, as you can see on your right-hand side, and that is a very useful technique to produce metal with refined grains microstructure and to give higher strength and ductility at the same time. Another technique is the cooling technique in the heat treatment process. For example, normalizing of carbon steel that I will explain you later on in the chapter that is related to processing and heat treatment. And now we can come to the summary of microstructures of metals. At grain boundaries, atoms are not arranged in a crystallographic order as compared to those in the grain interior, and that will give a variation in microstructures of metals. So metallography that studies the microstructure of metals is very useful for engineers in order to understand the metal microstructures and to predict its properties. And that the metallography involves cutting, melting, grinding, polishing, etching, and microscopy. As you can see from the relationship over here, that once we investigate the microstructure of the metallic components, we can trace back to its crystal structure and also relate to the processing or its mechanical properties that are related to engineering applications. optical microscope, and also scanning electron microscope or SEM are normally employed for microscopic examination. And finally, fine-grained metals are favorable and can be achieved by fast cooling, inoculation for the metal casting, and also crystallization and heat treatment for those metals that has been processed by working operation.